Something that we learned already about entropy is that it is a way to measure how the energy of a system is dispersed. How spread out is the energy? And from our experience, we know that the way in which energy gets dispersed is through collisions. When a really fast molecule slams into a molecule that's just sitting there, it will transfer some of its energy to that other molecule through that collision. Okay, another great example is billiards. So let this reset for a second. So you can kind of see the energy getting dispersed there. But here comes the cue ball with a lot of energy, but then through that collision, whammo, it disperses all of that energy. Okay, well, something else we know about this kind of process, when you have energy being transferred through collisions, that's essentially heat. That's what heat is. That's how something that is hot transfers its energy to something that is colder. That's how it transfers that energy from a hot object to a cold object, is through those collisions. So we have perhaps a way to write an equation to quantify the amount of entropy because it's related to the amount of heat, that energy that's transferred as heat. So the measurement of entropy, energy dispersal, can be related to heat. And it's related through this equation right here, okay? So the change in entropy of a process is equal to this amount of heat divided by the temperature at which the process occurs. Now this subscript here, REV, will describe what that is in the next slide. It's really just a technicality. It will really never come up again. But just to be totally accurate about this, it's not just any heat, it's what we call reversible heat. So what that means is if you carry out a change, such as adding energy in the form of heat, you must be able to back that up in the same way, okay? So after carrying out a change along a given path, like adding energy as heat, it must be possible to return to the starting point by the same path, taking away energy as heat. So that's technically what we mean by the reversible heat. But again, for general chemistry purposes, it will not come up again. That's just to be technically accurate about it. Okay, so here's an example calculation using the amount of heat that's transferred to calculate the change in entropy of a process. In this process, what we have is we have mercury freezing. All right, so the element mercury is a silvery liquid at room temperature, and the normal freezing point of mercury is negative 38.9. And its molar enthalpy of fusion is 2.331 kilojoules per mole. Okay, so again, this is kind of a Chem 1 review topic. We learned about the change in enthalpy when something changes phase. And if it was freezing, we, instead of just, I don't know why, but instead of using the word freezing, chemists and physicists have chosen to use the word fusion. So what's the enthalpy change when something freezes or when something undergoes fusion? Well, it's related to the amount of moles that are present, but it's 2.331 kilojoules per mole if the substance is mercury. And so we are asked, what is the entropy change when 50 grams of mercury freezes at its normal freezing point? All right. So the first thing to do is to say, okay, well, I know how to calculate that because it's related to the amount of heat that's transferred in this process. And something else you have to remember from Chem 1 is that, and you can kind of even get it from the units, right? The heat that's transferred is just an amount of energy. Well, that delta H is an amount of energy per mole. So one thing I need to do is I need to multiply that delta H by the number of moles of mercury that I have, and that will equal the reversible heat that I'm going to use in my entropy calculation. Okay, because what I just learned in the previous slide is that this change in entropy is equal to that amount of heat that's transferred divided by the temperature at which it occurs. So this kind of does it in all one step, which I don't like, but if I had the luxury of being in the classroom, this is one of the situations where I would just do it all on the whiteboard first and then show it on PowerPoint. But since we're not in the classroom, what I'll do is I'll just talk through each piece and part of the calculation. There it is. So first of all, what I'm doing here in the numerator, of course, is I'm calculating Q. So all of this is what you see right here, okay? So the first thing I'm doing is I'm taking this delta H value that's given to me, the 2.331, and I'm multiplying it by 1,000 in order to convert it to joules. And the reason why is because typically entropy changes are recorded in joules, not kilojoules. So that's one thing that I will do. And the reason why it's negative is because, you know, it's positive here that's given as a given, but remember that I'm freezing. So that's going to be an exothermic process. This is going to be a negative delta H because it's giving up energy, releasing it into the surroundings. So that's why it's a negative quantity. So I take that number that's given to me, I convert it to joules, and now the next thing I need to do is multiply by the number of moles. Well, that's what this part of the calculation is right here. I have 50 grams, and I just convert it into moles using the molar mass of mercury. And remember, that just comes from the periodic table. If you look up mercury on the periodic table, you'd see that it has an average atomic mass of 200.59. So that means that its molar mass is 1 mole of mercury is 200.59 grams of mercury. So I just use it to cancel out my grams of mercury. I have moles of mercury. All right, so now I have moles of mercury over moles of mercury. So that cancels, kilojoules over kilojoules. So that cancels, and I end up with units of joules. And then the other important thing to remember is this temperature has to be in Kelvin. So remember, the way that you convert a temperature into Kelvin is just that you add 273. So I take the temperature at which this process is occurring. So what is that? Well, it's the temperature that's given to us, right? In the negative 38.9, but also think about it. If this liquid is freezing, it's going to stay at that temperature until all of it has frozen. So that's the temperature that I'm going to use, the freezing point. So I just add that number to 273, and then you do all the math, and you get a negative 2.48 joules per Kelvin. And again, that should make sense. This should be a negative number because I'm going from a liquid to a solid. And remember that solids have less entropy than liquids. They're more ordered, they're more organized, they have less entropy. So that's why it makes sense that this is a negative change in entropy. So the delta S of this process is a negative delta S. All right. So this would be one of those problems that I have you guys do at the board, but I'll just talk through it. So it asks, well, what is the change in entropy when you're boiling 100 grams of water at 100 degrees Celsius? And so we're going to use that delta H of vaporization, okay, so that change in enthalpy that's required if I want to convert liquid water into gaseous water. And its value is 40.7 kilojoules per mole. And once again, I'm just going to use this equation. This delta S is the heat that's transferred divided by the temperature. Okay, so this one I do a little bit more piece by piece, which is good. So the first thing I'm going to do is I'm going to calculate the number of moles of water. So I start with the mass of water that I'm given, 100 grams, and I change it into moles by just essentially dividing by the molar mass. So 1 mole of water is 18 grams of water, so that turns into 5.55 moles of water. Okay, so the change in entropy is equal to that reversible heat divided by the temperature. And oh yeah, I still haven't fixed this, but this reversible heat is equal to the delta H times N. So that should be times the number of moles of water. Okay, I forgot to put that in. It's a typo. I'll have to fix it later. So that's how I calculate the reversible heat. I multiply the delta H of vaporization times the number of moles of water. Okay. All right, so that's what this calculation is right here. So this is my delta H, which is given, 40.7. And I multiply that times the number of moles. And you might be wondering, well, wait a minute, why didn't I convert this into joules like I did in the previous example? Well, you'll see, that comes later. And you could do it either time. But just convert it into kilojoules at this point. Moles over moles cancel. Moles over moles cancel. So I'll have amount of energy in kilojoules. And then the temperature is 373 because I know that water boils at 100, and you add 273 to that and you get 373. Okay, so that gives you 0.606 kilojoules per Kelvin. But as I said before, that's a pretty small number. Generally, you know, we like to keep our energy values within the, you know, the greater than 1, but not greater than 1,000 kind of range. And so we change this into joules per Kelvin by just multiplying it by 1,000 to get 606 joules per Kelvin. Okay. All right, so that's how you would use an amount of heat that's transferred to calculate an amount of entropy, the change in the amount of entropy. All right, now standard molar entropies. We're going to talk about how a lot of the work has already been done, and they put these entropy values into tables for you to use in calculations. And that's what we mean by a standard molar entropy. So anytime that you see this superscript degree sign on a thermodynamic quantity like an H or an S or something else, that means it was determined under standard conditions. And we'll talk about what standard conditions means in the next slide. But let's say that we have this perfect crystal right here. So these are atoms or molecules, and they're in a perfect crystal. Okay, and remember something that we talked about yesterday, that the third law of thermodynamics says that if you have this situation, you have a perfect crystal and you're at 0 Kelvin, so you're at absolute zero, that's when you have zero entropy. So there's absolutely no entropy associated with this crystal right here because we're at 0 Kelvin and it's perfectly ordered. It has no motion at all. So we would say that this has zero entropy. And so the idea here is that if you add any amount of energy to this at all, if you heat it up at all, so if you, then you're going to have positive entropy. So because it's necessary to add energy as heat to raise the temperature, all substances have positive entropy values at temperatures above 0 Kelvin. So and now something that I've already kind of talked about, but let's put it in our notes. The units for entropy are typically joules per Kelvin. Now that's different than the typical units for delta H values. Those are typically in kilojoules. So the important thing to remember is reconcile the two units before you do calculations. If you have a situation where you got to manipulate a delta, something with entropy and enthalpy, you got to keep in mind the fact that they have different units, joules versus kilojoules. So you will need to reconcile those two units. Okay, so back to this picture. This picture, like I said, is a situation where we're going to say we're at 0 Kelvin, and that means we are at zero entropy. That is the third law of thermodynamics. So now we're just going to increase the temperature a little bit, and notice that I've got more randomness. I've got disorder. There was movement. The energy was dispersed, right? The energy caused these atoms or molecules to disperse. So what that means is that really at any temperature above absolute zero, you're going to have a positive entropy. All right, so why do I bring that up? Because as I said before, these standard molar entropies, which have been put into tables, will always be positive values that are not zero. So they'll always be greater than zero, and they'll always be positive. And so all these substances have their own standard molar entropy that's been put into a table. The units are joules per Kelvin, and you will never see any of them that are zero, and you'll never see any of them that are negative. Okay, so just to be a little bit more specific about the definition, I said that that superscript degree sign means that it was determined under standard conditions. And so it's defined as taking the substance, 1 mole of the substance from a perfect crystal at 0 Kelvin to its standard state. And if it's a gas, 1 bar of pressure. If it's a solution, 1 mole concentration at the specified temperature. So every one of these tables will always have a temperature specified with it. Okay, so the standard conditions don't include the temperature, but the table will always tell you at what temperature these values were determined. And the time which you'll need them is in a situation like this. So we're going to do calculations with entropy. And particularly if you need to calculate the entropy change of a reaction, you're going to use this equation right here. And you probably saw a similar equation in Chem 1, but with enthalpy values of formation, delta H of formation, delta H sub F. Okay, it's the same form where you just add up the standard molar entropy values of your products in a reaction, and you subtract from that the sum of all your standard molar entropy values of the reactants for that reaction. And that will give you, if you do that math, if you do that calculation, you'll get the change in entropy for this reaction under standard conditions, okay? And don't forget that these n's, in this case, represent those balancing coefficients in your chemical reaction. All right, so let's do an example. So let's say that we have this reaction. We have the 2 moles of hydrogen reacting with 1 mole of oxygen to form 2 moles of liquid water. Okay, so we got 2 gases reacting to form this liquid water. And we want to calculate what the standard molar entropy change is in this reaction. Okay, well, this is a situation where you'll use this equation, which is on your equation sheet. You don't need to memorize this equation. You just need to know, where it is, when to use it, and how to use it. And so, like I said before, what we're going to start with is we're going to sort of expand this equation to take into account each product and each reactant. Okay, so that's what I did in this step. So this change in entropy for this reaction is the standard molar entropy of the product. In this case, we only have one product, it's water. And this 2 comes from the fact that I've got a 2 out here as a balancing coefficient. So that's what this 2 represents. So I will be looking this up in a table. This is a table value that I'll look up, and I subtract from that. So you subtract from the product, from the sum of the products, the sum of the reactants. Well, I've got 2 reactants. I've got hydrogen and oxygen. So here is the standard molar entropy that I'm going to look up in a table for my hydrogen, and I multiply it times 2 because it has a balancing coefficient of 2. And I add to that the standard molar entropy value that I look up from a table for oxygen. Okay, all right. So those values are going to be found. They're going to be found in the table. So that link that I just showed you in the previous slide, you would just look up those values in that table. Okay, this is a little bit out of sequence, so ignore this for now. But this is what I did in this step. I just looked up those numbers, okay? So one thing to point out, so the standard molar entropy value for water, you're gonna see that there's more than one row of information for water. And it's because it has the different phases of water. There'll be one for gas, there'll be one for liquid, there'll be one for solid. So make sure you pick the correct one. That's a common error that students make. So the 69.9 is the standard molar entropy value for liquid water. So make sure you pick out the correct one. All right, and then you just look up these other values in the table just like that, just like you did for water, and then you just do all the math. And again, make sure you know how to do this in your calculator. Use lots of sets of parentheses if that helps, or you can just do it in pieces and parts and write stuff down and do it in steps if you need to. But make sure that you do this correctly in your calculator. That's another common student error. Okay, so now let's go to this note. So it's a negative value, and the thing is that should make sense. Because remember we said in yesterday's lesson that gases have more entropy, they have higher entropy than liquids. Well, in this reaction, what I'm doing is I'm taking some gases and I'm creating a liquid. So that should be a decrease in entropy, and that is confirmed by the fact that we get a negative value for this delta S. Remember, the delta means the change. The change in entropy of this reaction under standard conditions is negative, because I'm going from 2 reactants with high entropy, because they're gases, to 2 moles of product that is liquid, so it has lower entropy. Get going for today. So like I said, what we're going to start with actually is a review example that we're going to use later in the lesson today. But I don't want to take it for granted that you remember how to do these type of problems, or that you've even seen how to do this type of problem. But it's real important for understanding what we're going to do today. So back in Chem 1, you learned how to calculate the enthalpy change, the delta H of a reaction, okay? And you did it using an equation that looks like this. Okay, so again, you find the delta H's of formation of all the products, and you add those together, multiplying each one by the number of moles in the balanced chemical reaction. And then you do the same for the reactants, and then you subtract that sum for the reactants from the sum for the products. And that gives you the enthalpy change for the reaction. itself. So I just want to do an example problem like that, and then we're going to use this data that we get later in the lesson today. So it's a simple reaction. It's just a combustion of hydrogen. I think, in general, people understand that hydrogen gas is combustible, like a hydrogen balloon. It's an explosive gas, and so we know that it happened that this reaction occurs spontaneously. If you have hydrogen gas and you have oxygen gas mixed together, and you just a tiny little spark, the two will combine and they'll form liquid water. So we know that this reaction occurs spontaneously. So what we want to do is we want to calculate the delta H of this reaction. And remember what this means. This superscript means it's under standard conditions, okay? And the table values that we're going to use are specific to a certain temperature, and usually that temperature is 298. So that's the reason why we have the 298 in the problem statement. Okay, so now we're just going to apply this equation to calculate the delta H of this reaction to the different pieces and parts of the reaction. So the first thing I need to do is I need to look up in a table all these delta H values of my products and subtract from that the sum of all the delta H of formation from the reactants. Okay. So we're going to just expand this equation out. So there's only one product, just water. So I just need to look up that delta H of formation of water, and I multiply it by 2 because there's a coefficient of 2 in this in this balanced chemical reaction. So I'm going to do that for each one of these reactants as well. Now, if you're clever and you remember that because these are pure elements, pure hydrogen, pure oxygen, their value is actually 0. So you could save yourself some time if you remember that fact. Okay, but that's what you would see in the table for hydrogen and for oxygen. So you just do the simple math here. 2 times a negative 285 is a negative 570. So the enthalpy change for this reaction is a negative 570 kilojoules per mole. And again, that should make sense because we know that just from our experience that this is a combustion reaction, so it should release energy, you should get heat out of it, right? And that's why it's a negative number. Negative means it's a release of energy into the surroundings. Okay, so we get into the surroundings 570 kilojoules per mole of the reaction that's occurring. Okay, so hopefully that, if that's the first time you've seen that, hopefully you understand it, or if you had this information in Chem 1, hopefully that reminds you how to calculate these values. Okay, because like I said, we're going to use this today. All right, now we're getting into we're still in lesson 2, so this still is the fill in the blank handout sheet from lesson 2. And remember that the universe is composed of a system and surroundings. And so the entropy change, the standard entropy change for the universe is just the sum of the entropy change of the system plus the sum of the entropy change for the surroundings. Okay, it's just by definition, that's what we mean. Now, that's an important definition because of the next point. And that is, we are going to say, and this is the second law of thermodynamics, just kind of said in a slightly different way, any process that's spontaneous will give a positive value for the delta S of the universe. So a process is considered to be spontaneous under standard conditions if the delta S of the universe is greater than 0. Okay, so when we add these two numbers together, if we get a positive number, that means that this is going to be a spontaneous process. All right, so now the other thing that it's important to recognize is that if it happens to be 0, if when you add these two together, if you get an answer of 0, then what that means is you're at equilibrium. Okay, so two important things to remember about delta S of the universe. If delta S of the universe is positive, it means you have a spontaneous process. If delta S of the universe is 0, it means you're at equilibrium. Okay, so now we're going to go through calculation for the surroundings. Okay, and we're actually going to derive an equation for that because it's difficult to actually directly measure what's going on in the surroundings, right? It's easy to measure what's going on in the system. I just stick a thermometer in my beaker, right, or something like that. But what's going on with the surroundings is a lot more difficult to determine, in large part because remember what the surroundings is. Okay, go back here. The system is something we can isolate, but the surroundings is just everything else. Okay, so that's why it's difficult to really figure out what the delta S of the surroundings Is. So what would be nice is if I could relate the delta S to the surroundings in some way to something that's going on in the system. All right, and that's what this relationship helps us to do. So just by definition, we learned this on Wednesday, that a change in entropy is equal to the amount of heat divided by the temperature, the amount of heat that's transferred divided by the temperature. So the change in entropy of a system is just the amount of heat going into or out of the system divided by the temperature. And you could say the same thing for the surroundings. The change in entropy of your surroundings is just the heat transfer to or from the surroundings divided by the temperature. All right, so we're gonna have to invoke something else that we learned back in Chem 1, and that is this law of conservation of energy, the first law of thermodynamics, the law of conservation of energy. It says that whatever heat is gained or lost by the surroundings is the same but opposite in sign to the heat gained or lost in the system. The same magnitude but opposite in sign because energy is conserved. So that's important because that allows us to make a substitution so that we can translate from talking about the surroundings to start talking about the system. All right. So now, one thing that we need to keep in mind is that if you, these are all standard quantities that we're after. So they are typically per mole. So that's the first thing I want to recognize. If, I'm going to take the amount of heat that's being transferred, I'm going to divide it by the number of moles of the stuff, of the substance that's involved. Okay, so it would be the Q system divided by the number of moles. And that's equal to the delta H of the system. Because remember that at a constant pressure, the heat that's transferred at a constant pressure is equal to the delta H. And I'm just going to divide by number of moles because, again, the values that we find in these tables that we're going to be using are always per mole. So the heat that's transferred to or from the system per mole is going to be equal to the enthalpy change of the system under standard conditions. Okay, so now we're just going to substitute in this relationship. Okay, this Q system is just going to be the same as negative of the Q surroundings. Okay, so the negative of the Q surroundings divided by number of moles equals the delta H of the system. You see what I did there? I just made that substitution based on the first law of thermodynamics. Okay, and so now I'm just going to move this negative sign. You can do that. Just divide both sides by -1, gets rid of that negative, and it makes this negative. So the Q of the surroundings per mole is just the negative of the delta H of the system. All right. So there it is. I translated what's going on in the surroundings into something that's going on with the system. And that's what my goal was. So now we can say that the change in entropy of the surroundings is equal to the negative of the delta H of the system divided by the temperature. And the reason why that's important, again, is because it's much easier for me to tell what the delta H of the system is. Okay, that's much easier to determine. Finding out something about the surroundings is very difficult. But if I can just measure, for example, a temperature change in the system, then I can figure out the delta H of the system, and then the negative of that delta H of the system divided by temperature is the change in entropy of the surroundings. Okay, so really all this slide is just kind of to derive this equation right here. That's what the whole point of this slide was. All right, now, here is an example problem. So what we want to do is we want to calculate the entropy change of the surroundings for the same reaction that we started with, the 2 moles of hydrogen reacting with a mole of oxygen to give us 2 moles of liquid water. Okay, so we already did this calculation. We figured out the delta H of the reaction, and in this case, the reaction is the system. So we could also say this is a delta H subscript SYS for system, because in this case, the system is a reaction. So the delta H of the system, we already calculated this, is a negative 570 kilojoules per mole. I forgot to put the per mole in there, but it should be per mole. Okay, well, I just derived this relationship. The delta S of the surroundings, which is what we're after, calculate the entropy change of the surroundings, right? It's just the negative of the delta H of the system divided by temperature. By the way, I'm still catching these. The last textbook that I taught out of put the subscript R on the left instead of the right, and I'm still trying to find those to fix it. It's just a notation thing. It means the same thing. So this is the symbol for the delta H of the reaction, the same way that this is the symbol is the delta H of the reaction. I'll try and fix it before I post this PowerPoint in Blackboard, but I'm still catching the instances where I haven't changed it yet. But it means exactly the same thing. Okay, so essentially I'm going to take this number, I'm going to put it here, and I'm going to divide by the temperature, which I know is 298. Okay, so the delta S of the surroundings is just the negative of the negative 570. So here's your negative in the equation. Here's my negative delta H value. I divide by 298, and you get 1.913 kilojoules per mole Kelvin. Okay, but remember that entropies, delta S's we typically express in units of joules, okay? So I'm just gonna go ahead and convert that into joules. In one, there's 1,000 joules, 1 kilojoule, so kilojoules cancel, and that means I have 1,913 joules per mole Kelvin. So that is the entropy change to the surroundings, okay? So not the entropy change of this reaction, it's the entropy change of the surroundings. All right, so this is a follow-on question. So now we want to calculate the entropy change for the universe for that same reaction. So previously, we said that the delta S of the surroundings was 1913 joules per mole Kelvin. That's what we did in the last slide. So we also know that the delta S of the system is negative 327 joules per mole Kelvin. I think that we calculated that on Wednesday, right? So that's part of the reason why you may need to go back and look at that lesson again, that PowerPoint again, but this was something that we calculated on Wednesday. So just now to calculate the delta S of the universe is I just put those two numbers together, okay? Because the delta S of the universe is just the sum of the two, all right? So when I add these two numbers together, you get 1586 joules per mole Kelvin. Now, the significance of that, why do we even care what that number is? Why do I care what the delta S of the universe is? Well, because that is an indicator of whether or not the process is spontaneous. If it's a positive number, like it is here, then it is a spontaneous process. And so, yes, this delta S of the universe is a positive number, so it means that this is a spontaneous process, okay? So this is one way to indicate whether or not you're gonna have a spontaneous process. If, when you calculate delta S of the universe, if it's a positive number, it means that you have something that will occur without, you don't have to force it to occur. It just happens naturally. And in this case, you got to put in the caveat, under standard conditions. That's what these superscript degree sign mean. Okay? All right. So that's the whole purpose of calculating delta S of the universe, is so that you can figure out whether it's going to be a positive or a spontaneous or non-spontaneous process. Okay. So, but the other interesting thing about it is that in this problem, we calculated that it was spontaneous, okay, because it's greater than 0. So the entropy of the universe increases. Therefore, the process is spontaneous under standard conditions, okay? But this is the interesting thing. So it's a process that's spontaneous due to the entropy change to the surroundings and not the system. And think about that. What you're doing is you're taking two gases and you're creating 2 moles of a liquid, right? And the second law of thermodynamics says that, hey, spontaneous processes are those that increase entropy. Well, you're not getting more entropy out of this reaction itself. I mean, with these two substances, when they combine, they actually go down in entropy. This was a negative entropy. It was a negative 357 or whatever it was, right? Let's see what it was. Yeah, negative 327, okay? So that reaction actually had a decrease in entropy. And then, again, that should make sense because we're going from gases to a liquid. But when you do this reaction, when this reaction takes place, it increases the entropy of the surroundings so much that it actually makes the overall entropy change to the universe positive. Okay, so it's not so much what's going on in the reaction itself that makes it a spontaneous process. It's what's going on in the surroundings that make it a spontaneous process. So that's kind of interesting, and you see that every once in a while in nature. Okay, so let me just do one more example problem for you. This is just another combustion reaction. In this case, we have methanol, okay? And it's reacting with oxygen to give us the normal products of combustion. Normally, when you burn something that's carbon-based, you get 2 products. You get carbon dioxide and you get, so once again, we want to calculate the entropy change of this reaction. And the way we're going to do that is we'll add up all the standard molar entropies of the product. So we'll look those up in the table for these 2 guys right here. And then multiplying them by the coefficients. So 2 times the standard molar entropy of the carbon dioxide plus 4 times the standard molar entropy for the water. And that's what we'll do here. And then we'll subtract from that the sum of the standard molar entropies of those 2 reactants, okay? So if you do that, you get these numbers, okay? Just found those in a table and you do all the math and you get that the standard, the standard entropy change of this reaction is 313.25 joules per Kelvin. And again, that should make sense because this is a liquid and you're creating a lot of gases, 6 moles of gas, 2 moles of gas there, 4 moles of gas there. Okay, this is water in the gaseous phase. So you're creating more gas. So you should have a positive entropy change. All right, so that is the delta S of this reaction. Okay, and if you're writing down these numbers, I'll pause a second. Next thing is we need to calculate the delta H of this reaction. Because we know that we're going to need that to calculate the delta S to the surroundings. Okay, so the delta H of the reaction is like we did at the beginning. You look up the delta H's of formation of these products from the table, and you subtract from that the sum of the delta H's of formation of these reactants. Again, remembering to multiply times the number of moles each time you look up one of those values. So again, you look it up in the table, and if you want to, I'll pause a second to let you write those down. Okay, so you just do all the math. Oops, and you get a negative delta H. And again, that should be pretty, it should make sense, because what is this? This is a combustion reaction. Why do we do combustion reactions? We do it to get some sort of energy out of it, right? So that's why this makes sense that it's a negative number, because when this occurs, it releases energy, and we utilize that energy to, heat something up or to, for some other purpose, okay? So this is the delta H of the reaction. And the reason why I calculated that is because now I want to calculate the delta S of the surroundings. And I know there's that relationship between the delta H of between the delta S of the surroundings and the delta H of the reaction, okay? So I just figured out that the delta H of the reaction was negative 1277. And so this is occurring at 25 Celsius, okay? And remember, I got to change that into Kelvin. That's the only other curveball you got to think about in this particular problem. So I make that substitution. The delta S of the surroundings is the negative of negative 1277 divided by 298, okay? And because it's an entropy value, I don't want to keep it in kilojoules. I want to go ahead and change it to joules. So you get that in joules, and it's 4280 joules per Kelvin. And again, sometimes I forget to put the per mole in here, but I'll have to fix that later. But remember that these are per mole. So there should be mole in the denominator, mole in the denominator. Same thing here, mole in the denominator. All right, so now I know the delta S of the system, and I know the delta S of the surroundings. Okay, so I can put those two together. So I can calculate the delta S of the universe by just adding those two values together that I just determined. Okay. So you put those two numbers together, the 313 and the 4280, and you get a very positive value for the delta S of the universe. It's greater than 0, so it is spontaneous. Okay. All right, so I think that we'll stop there. So if you already did 5 and 7, you can now do number 6 in the homework assignment. But if you have not done 5 and 7, you could also attempt, based on lesson 2, the whole of lesson 2, questions number 5, 6, and 7 from the homework assignment.